For the next few minutes, we're going to look at how to reverse the process of taking the derivative, or what we say, finding antiderivatives of functions. And we know how to do a lot of derivatives. Let's start off with some of the basic ones that we know how to do. For example, if we have a function, we'll make a table here, so on this side we'll put a function. So suppose the function is y equals 3, then the derivative of a constant is just 0. If the function's, for example, x, then the derivative is just 1. If the function is 2x, then the derivative is 2. If the function's a little more complicated, so for example x squared, then remember we do the power rule, so we take the 2 down and minus 1 from the power, so we get 2x for the derivative. Let's keep going just a few functions more. If we have the function x squared plus 2, then we take the derivative of the first thing and the derivative of the second thing, so the derivative of x squared is 2x, and plus the derivative of 2, which is 0. So in other words, the derivative is still 2x. Notice these two functions have the same derivative, 2x. And we'll do one more. If the function is x cubed, then the derivative is 3x squared. So now what we want to do is reverse the process. So I'm going to give you the derivative of a function, and your job is to find what the original function was. And in fact, we can do this just by looking at this table backwards. Let's go over here and make a corresponding table. If I say that the derivative of the function was 0, well, the function could be 3, like we saw in this table, but there's other functions that have a derivative of 0. So it could be 2, could be 1, could be really any number, any constant. And so we'll just say that its antiderivative, the original function, is a constant c. So this c means a constant. Any constant. Alright, so what if the derivative is 1? What's the original function? Well, we see from this table over here that the original function could be x. Are there any other functions that have a derivative of 1? Take a second to think about it. Well, here's one function that I thought of that had a derivative of 1, x plus 2. And another function, x plus 5. And you can see yourself that you can take x plus any number, any constant number, and you'll always have a derivative of 1. So we write the antiderivative as x plus c, where again c is just a constant. We aren't specifying what it is, we just put it there to remind ourselves that the original function has the form x plus a constant. And if I said, well, that the original function, or the derivative of the function, is 2x, what's the original function? Well, we can see from, I'm looking at my table wrong. If the derivative of the function is 2, then the original function could be 2x. It could be 2x plus 1, and again I can add any constant I want, so in general I say 2x plus c. Now I'm going to circle or square the most general forms of the antiderivative, or the opposite of the derivative. If I give you the derivative, this is called the antiderivative right here. Alright, let's go down our table one more. This table becomes a key to finding antiderivatives. If the derivative is 2x, then the original function, well, could be x squared. So what this says is, again, the derivative of x squared is 2x. So the antiderivative of 2x is x squared. And I could also add in any constant I want, just like I did in these 3 examples up here. So I'm going to write x squared plus c as the general antiderivative, the form of all possible antiderivatives. And let's do one more. That is 3x squared So what's the antiderivative of 3x squared? Well, I can look over here and say if the derivative is 3x squared, then the original function could be x cubed. Or it could be x cubed plus 1, or x cubed plus 2, or x cubed really plus any number. So again, I'm going to represent it by x cubed plus a constant. Now there's a little bit of notation I'll introduce that we use to say take the antiderivative, or in other words, if I give you a derivative, tell me what the original function looks like. And that is a sign that looks like the summation sign that we saw from last time. Let's, for example, write this fact right here. This fact is written as the antiderivative of 3x squared, and then I'm going to put a dx. This signifies that x is the variable that I'm doing the derivative with respect to, or the antiderivative with respect to, is x cubed plus c. So this sign right here is called an integral sign, and it means take the antiderivative, and so take the antiderivative of this function that's in between the integral sign and the d variable name, and we call this variable name, again, the dummy variable, just like we did in class the other day. And this notation, the integral sign, some function, dx, just means find the function that has a derivative of 3x squared. So in other words, the derivative is 3x squared. I want to find what the original function is. And in this case, the original function is x cubed plus c. And we can always check our work by taking this function and taking its derivative, and we should end up with what we have inside the integral. So for example, x cubed plus c, I go down here and I say, well, the derivative of x cubed plus c, that's x cubed plus a constant, is 3x squared plus 0, just 3x squared, and this 3x squared is what I had inside the integral sign. So the antiderivative of 3x squared is x cubed plus c.